Welcome to Science at Work, a new podcast from Savannah River National Laboratory in Aiken, South Carolina. I'm your host, Mike Edelmeyer. Science at Work is a production of the Savannah River National Laboratory, SRNL Office of Communications. We usually start the podcast with a celebration of sorts because this year is quite special for us. It's been 20 years since the U.S. Department of Energy designated SRNL as a national lab. But if you've listened to our show before, you would have heard that our legacy spans 7 decades to back in the early 1950s and the Cold War. We're trying to pull back the curtain, if just a little bit, on what a national lab is and what it does. This month, and with each episode to varying degrees, we'll discuss how SRNL puts science to work to protect our environment, serve our national defense, secure our clean energy future, and reduce emerging nuclear threats. And what better way to do this than to interview the scientists, engineers, and other professionals who are at the heart of who we are and what we do. Today we'll speak with Vincent DiNova, a staff engineer in the Instrumentation, Robotics, and Imaging Systems group here at SRNL. Vincent's research is applicable to national defense as well as advancing fundamental science. Why is this important? Well, for many reasons. Vincent will get into that in a little bit. He impressed us last year during a TEDx-style talk about his work for SRNL's first Research Slam, a science communications competition. Now, this might sound less than fun at first glance or first listen, but I can tell you that it really was a lot of fun because the presenters weren't giving lectures. They were on stage to inform and entertain an audience in a small theater and had just 3 minutes to do it. But before we get into Vincent's research, let's get to know him a bit. Thanks for joining us today, Vincent.
Absolutely. Thanks for having me.
Tell us about the Instrumentation, Robotics, and Imaging Systems group here at SRNL and what you do as part of the group.
So we have one of the longer titles for any group on site, which is nice, and it really is broken down into what we do. So a large part of it is the instrumentation part. We have field deployable systems all throughout the site and for all of the directorates. So we make custom-made systems for our environmental legacy management cleanup efforts. We have systems that are field deployable for our Global Security Directorate as well as our production sites. My overarching organization is the weapons production technology, so a lot of our future efforts are going to be in that. And one of the emerging parts that we're getting into is the robotics. A lot of the application space that we have right now are for environmentally, cleanup efforts. And those cleanup efforts take human capital. And one of the big things when you talk about safety is reducing the radiation risk to employees. So any automative effort, any robotics that you can introduce to replace a human will help drastically reduce that. So that's a huge effort that's been going on in our group. And then the portion that I work with is actually in the imaging systems group, or portion of the group. So we have camera systems that are deployed all throughout the site for different safety reasons or monitoring reasons. But what I do is actual X-ray imaging. And so since the early onset of digital imaging, we've been at the forefront with either camera systems or flat panel detectors, and we make CT systems not too dissimilar from what you would get if you went to a hospital and needed to get an X-ray.
Ah, okay. Makes sense. Great. Just to step back a little bit, where did you attend college and what did you study?
Yeah, so my background is actually a little bit different. So I went to NC State for all 3 degrees, which they say not to do, but I did. Our nuclear engineering program is number 3 in the country, and so I decided I didn't want to go to number 1 or number 2, so I just stayed there. And my background was in nuclear engineering, like I said, and my main focus was actually on detection applications. And what sort of brought me to SRNL was they said, X-ray CT is an application in X-ray detection, and I said, great, let's do it.
Well, that's cool, and that was my next question. What brought you here? So, can you maybe expand a little bit more on so the X-ray imaging? I found that real interesting when you were talking about that in the Research Slam, which I mentioned earlier. You mentioned something about shadow puppets, which I thought was kind of a cool way to kind of start it.
Yeah, so I'm a layman of sorts. I like breaking things down about as simply as possible, and so I like 5-second clips, 30-second clips, and then 30-minute clips. So those are sort of my talks. Like, how do I get somebody's attention if they know nothing?
Yeah.
How do I give them enough of an idea that if they are interested, I can give the 30-minute talk?
Yeah.
Which as scientists is what we like to do, is to go to, big conferences and give the larger talks. And so the most reduced down version of it is I make shadow puppets and do arts and crafts.
That's great.
And it almost always elicits the question, well, tell me more. What does that mean? And very similar, everybody knows what shadow puppets are. Instead of light, which is a wave and a photon, we have higher energy photons in the form of X-rays. And what that affords us is that we actually get through the part in some respects. And we measure the difference in how many make it through the part versus not through the part, or different parts of the part. And that informs us as to what the interior of it looks like. Okay. And so the great thing about it is that we can see inside of something without actually changing anything about it. So it's a completely non-destructive technique. You can take your part, put it in, shoot it with some X-rays, bring it out, and it's the same as it was before you ever put it in.
That's great. Okay. Sounds highly useful to be able to do that. You're listening to Science at Work, a new podcast from Savannah River National Laboratory. We're speaking with Vincent DiNova, a staff engineer with a PhD in nuclear engineering who works in the Instrumentation, Robotics, and Imaging Systems group. Vincent, can you tell us, how your research may impact our listeners?
Absolutely. So basically anything that you interact with, any component, any materials, they have failure modalities. So one of the things that we look at is we have a part that fails and we want to see why. Maybe you have a valve that catches, or maybe you have an electronic component that has stopped working. You plug your lightning cable into your Apple, device, and it no longer charges. Well, we can stick it in and inspect it with X-rays and see if one of the cables is broken, or if one of the prongs on the inside of your phone is broken, and inform how to repair it if you can repair it, or tell you if you need to replace it. So we have lots of parts that we look at. The biggest one that's really an expanding part of our portfolio is really in additive manufacturing. And additive manufacturing has been around for decades and decades now, but we're sitting at a table that's not additively manufactured, talking into microphones that aren't additively manufactured. I don't see anything in this room that's additive manufactured. So what have we been doing for the last 20 years? Yeah. Why is there not additively manufactured parts all around us if it's this new groundbreaking technology? It's not in our planes, it's not in our cars, it's not in our day-to-day devices. And one of the big reasons for that is, we have hundreds of years of experience on traditional materials and traditional manufacturing. And we're getting that experience and exposure with additive manufacturing, but we still haven't quite figured out the best ways to inspect those. And really, again, as a non-destructive evaluation or testing group, we are trying to develop the tools so that we can better inspect and evaluate the final part that's coming out of the additive manufacturing processes.
Okay. And so in terms of additive manufacturing, we hear a lot about 3D printing technologies and things like that. Does 3D printing have a role in additive manufacturing, or is that a piece of it? Is that a big piece of it?
So
a small piece?
They're actually the same thing.
Oh, they are. All right.
Yeah. So
Okay.
The academics like to refer to it as additive manufacturing. 3D printing is more the hobbyist kind of.
That's true.
They went through a nice little PR spin, which is always good to do. You'll also sometimes hear rapid prototyping.
Yes.
Which is a bit of an offset. Usually that's to build scaled down versions of something so you can go through, faster testing processes and then traditionally manufacture the final part.
That's right.
So you can go through those iterations at a faster level. And I think that some of those things are also kind of what holds it back, is a general rule, because there's almost like this psychological barrier that everybody says, well, I've seen rapid prototyping stuff. It's not as good as the real stuff. Or I know 3D printing. My cousin's a hobbyist and, makes Star Wars figurines in his house. And there's a big difference between, those kinds of activities and a true additive manufacturing.
Sure.
And another component that holds it back as well is when we manufacture something, we have a widget. We try to make the same exact widget with additive manufacturing processes. But one of the major advantages to additive manufacturing is that you have access to every voxel in a volume. So you can make something that you couldn't actually manufacture by subtractive methods. And so one of the big focuses that we have are on lattice structures. So you have a full large part, and you subtract from the middle of it and have complex interwoven lattices. And the advantage of that is that it gains you a lot of the mechanical properties that you would lose if it was hollow, but you reduce a lot of the weight. So if you're in a aerospace application, or if you're driving a sports car and you want to drop, 50 pounds because it, makes you that much faster or reduces that much fuel load, it becomes very, very applicable in a lot of those spaces. And especially if you're trying to send something into outer space, you have heat shields and you've got, all these really heavy components. Well, that's a lot of extra fuel that you have to have on your rocket, and that's where all your waste goes to. So if we can reduce down some of the weight burden from the space shuttle itself, it makes it much more affordable to have space tourism one day, and, be able to vacation in a hotel in the sky.
It's amazing. In terms of additive manufacturing, the possibilities for that and the applications of that throughout industries seems almost limitless.
Yeah, I mean, I wouldn't necessarily go that far.
Mm-hmm. Okay.
With every technology, you sort of see that. AI is the big one now. There's this big hype space, and we're throwing it at everything. And I think in 5 years, we're going to look back and go, oh, well, it was great for these things. It doesn't work as good over here. And they've sort of gone through different cycles of that within the AM community or additive manufacturing community. I think polymers or plastics have had a really good run and a lot of success, even more so than a lot of the metal printing that we're seeing. There's also ceramics that are starting to emerge and come into the same place. So there's a lot of different competing technologies and different application spaces, and they're going through their own little, hype and rise and fall of where each one sort of fits in. And yeah, the possibilities are sort of limitless. It'll sort of take the next generation of designers to be able to unlock what you can actually do. Because a lot of times if I'm making the same part traditionally or additively, you're going to outperform with the traditional manufactured part almost every time. Okay. But if you can think about how to redesign something so that it's actually different, what does that unlock? If you have structural components that have lattice patterns to remove waste or weight, that is very valuable and useful, and you can't manufacture that a different way. Right. So when the designers get their hold, they can really think about, can we change what the cabin of an airplane looks like? Can we, change what the shape of a car looks like, or the way that we design, the drivetrain, or, whatever component it is that they're looking at. But they really need to think about it in a way that you couldn't make it otherwise. Otherwise, traditional is going to largely outperform.
So there's really a lot more to this, and a lot more that we have to think about going forward with additive manufacturing, and the jury's out, so to speak, on I guess the best use cases for that versus traditional manufacturing methods, right? To put it very simply. So you probably started getting into this a little bit, but what can you tell us about the future of your area of research? Sort of what's next?
Yeah, so we've been, again, very heavily involved in the additive manufacturing process. Some of that's on the material side. So we'll do very high magnification shots to help the material scientists look at porosity or cracking so that they can hone in on the printing parameters that makes the best material that they possibly can. And then also, if you think about once you get that honed in, you get the processes of the printer, well, now you can start making the parts.
Mm-hmm.
And this is where we really identified that there was a huge gap in the technology. So there's commercial products that do RCT reconstruction. So we take hundreds or thousands of two-dimensional images and then do a reconstruction. So we take all the geometry within our booth, and then we trace how all the x-rays are going through the part and to the detector, and then we can back project and render what a 3D rendering of that object would be.
Okay.
Now, the main company that has the software, I think they have something on the order of 90% of the market share. Everybody uses it, is Volume Graphics. And it's a wonderful program for what it does. But it doesn't have any real capabilities for any of these complex geometries. So if you introduce a lattice pattern or any other kind of complex internal structure, it wasn't designed for that. And so we've been working on some of the technology, some of the tools that would be needed to evaluate these things. And again, it's sort of a moving goalpost as well, that we don't necessarily know what kind of designs are going to be out there. So we're trying to figure out what's common now, what's coming down the pipeline, and making sure that we've got tools developed so that in one of our sister production sites or one of our other sister national labs, if they design a part that has a gyroid or a truss style lattice or some other complex shape, that we have an analysis suite that they could then throw at it and not be relying on a software that's just not going to give them the answer that they're looking for.
Vincent, in addition to getting to know you and your work at SRNL, we also like to get to know you, the individual. That's always fun. So what is one thing we should know about you that influences the person you are and your approach to your work here at SRNL?
I got a limit to one thing?
Well, you don't have to. You don't have to, but, I thought we would start with one.
Sure. So I've actually, me and my girlfriend just hit 8 years. We just had our 8th anniversary.
Nice.
And I came into this relationship. She had a son who was born with Down syndrome.
Okay.
And so a big influence in me right now, and a big motivator for me is making sure that my successes aren't my successes anymore.
Mm-hmm.
Right? Having somebody to share in successes, it makes everything so much better. I was in a conference last week in Denver, and she was able to come with. She actually snuck in without any credentials and sat in the back and got to watch. And I mean, she was just delighted to hear me, do what I do, out in the world. And then, I mean, if we really want to go back, I mean, my parents are probably the ones that, shaped, me more so throughout my whole life. And there was actually a thought that I had during the research slam, and I guess this is probably a decent time to share it. So my mom was a career Navy. She was in the United States Navy for 27 or 28 years, retired as a full bird captain, so the same as a colonel if you were in one of the other branches. So really respected, really great career. She had her background in physics. She ended up getting a master's in the Navy in nuclear physics. I sometimes say that I got a PhD because I'm competitive and wanted to one-up her. And in high school, I was trying to figure out what I want to do. And, I saw, her career path and what she did. And I was like, I'm just going to, piggyback off of that. And she says, well, physicists don't get paid anything, so go be an engineer. So I did nuclear engineering. That's literally how I, sort of fell into the career. And I was even in Navy ROTC scholarship. I changed it to a Marine Corps scholarship in college, and then had a heat stroke. And was subsequently dropped from the program, and that's what sent me to grad school. Actually, the financial collapse happened my last semester of senior year, so I said, "Oh, okay, fall of 2008 is not the best time to graduate." But so very, very intelligent woman. Early part of her career, joins the Navy. They sent her to be an instructor at the nuclear Navy school where all the submariners and surface nukes go. And then after that, that's actually where my parents met. My father was in her class, which probably breaks a couple rules, but nothing happened to them. They didn't get thrown to Leavenworth, so I guess it was good enough. And then so she ended up going to postgraduate school, and then she went to work in D.C. doing some R&D up in the D.C. area. And then the Navy said, well, we don't let women on submarines or ships or aircraft, so your job is to now be in recruiting. And to see her continue her career and progress to the level of captain without the opportunities, wasn't sort of lost on me. And this is where I'll bring it back to the research slam. I was sitting there. She was going through some medical stuff. She was actually in attendance in the audience. And so my parents got to see it, which was also really exciting. And I saw the 8 of us, and I think we had 2 women, yes, 1 Hispanic, 2 African Americans, and it wasn't lost on me that when we talk about diversity and equity and inclusivity, that we sort of achieved it at that moment, right? Like, they had the opportunity. They presented tremendously well. Sean went on to win in D.C. Those opportunities weren't there, 30, 40 years ago when my mother was starting her career. And having those opportunities now is just, that's everything, right?
Yeah. Oh, that's great. Well, I'm glad I asked the question, because that's a good story. That's a really good story. Vincent, thanks for being with us today and sharing your expertise. It's really important to hear about. And thank you all for listening to our podcast. Science at Work is a production of the Savannah River National Laboratory in Aiken, South Carolina.